Bismillahirrahmanirrahim. We concluded from our consideration of the stress tensor that 9 components completely describe the state of stress at a point. Now, are these stress components independent of each other, or do some of them have a relationship with one another? It turns out that barring very special cases, which we don't need to go into for our purposes, we can further reduce the number of components that completely describe the state of stress at a point. We are going to show in this segment that the stress tensor is symmetric. In other words, the shear stresses tau ij are equal to tau ji. That is, tau xy is equal to tau yx, tau xz is equal to tau zx, and tau yz is equal to tau zy. This makes our life simpler because we need only to figure out 6 stress components instead of 9 to completely know the state of stress at a point. Let us start with a cube of finite dimensions, delta x, delta y, and delta z. Note that this is not yet a point, although we will soon ensure that it converges to 1. We are going to use the equilibrium moment equation about line OZ, this line. That is why only stress components that will contribute to this moment have been shown to avoid clutter. Since it is finite dimensions that we have started with, we cannot talk about stress at a point, hence the use of asterisks to indicate that stress on any given phase is variable and we are only taking its average value. This average value is assumed to act at the centroid of each phase. The body forces, similarly, dx and dy, act at the center of gravity of the cube. Also note that since it is not a point yet, we use primes to differentiate between stress components on the planes passing through the origin and their counterparts, distance delta x, delta y, and delta z apart. Note that stress components on this space, and this space have primes on them because they are different from the corresponding components on the planes that pass through the origin. Now let us write down the moment equation in vector form. Now taking cross products and dividing by the volume delta x, delta y, delta z throughout. Rearranging the terms. Now let delta x, delta y, and delta z approach 0. That is, converge to a point. And let's also recall that at a point, we can dispense with the asterisks as well as the primes. Therefore, the equation becomes these terms cancel out, and we are left with or. Now, taking moments about the OX axis and about the OY axis, it can similarly be proved that tau yz is equal to tau zy and tau xz is equal to tau zx. Which means that the cross shears at a point, that is, those on planes at 90 degrees to each other, are equal. That is, tau xy is equal to tau yx, tau xz is equal to tau zx, and tau yz is equal to tau zy. Also, both must be directed either towards the corner or away from the corner. This last statement can be made because we did not get a minus sign in the equations. Tau ij is equal to tau ji. Now, this property of the stress tensor is called the complementary property of shear. It is not an intuitive property. We have only figured it out mathematically from equilibrium considerations. But now that we know it, we will make extensive use of it in our investigations of stresses. As a result of the complementary property of shear, the stress tensor can be represented as or simply let's take up a problem now. Let's first express the state of stress as a stress array. We have the normal stress components. Let's write them in their respective places. Now let's take up the shear stress components. Tau yx minus 1, tau yz 2, tau zx 0. Now we know the stress tensor to be symmetric, so we can fill in the rest of the places based on that. We have the state of stress expressed as a stress array. That's never a problem, provided one knows the 6 independent stress components. Let's not forget to write the units here. Now expressing the same state of stress on a point graphically, let's take up the components one by one. First take up the normal stress components. Sigma x is 3 megapascals. Sigma yy 2 megapascals. Sigma z is 0, no need to show that. Now we take up the clear components, tau xy or tau yx. They're always the same and they have negative signs. So let's draw them in their negative senses. This is tau xy in the negative sense, and this is tau yx in the negative sense. Both of these are and they are both of them shown in the negative sense. Now tau yz and tau zy, again both are same. This is tau yz shown in the positive sense, and this is tau zy shown in the positive sense. Finally, tau xz and tau zx, they have 0, no need to show them. Again, to avoid clutter, we have only shown the stress components on the positive x, y, and z faces. We have corresponding stresses on the negative faces as well.